Welcome back to the deep dive. Imagine unlocking the secrets of a whole new class of chemical compounds molecules that seamlessly bridge the divide between organic and inorganic chemistry. These aren't just academic curiosities, They're the unsung heroes driving everything from the plastics we use daily to the advanced sensors in medical devices. Today, we're plunging into the fascinating realm of D-metal organometallic chemistry. This field is it's a constant source of new reactions, unusual structures, and practical applications that truly impact our modern world. We've taken a close look at Chapter 22 of Shriver Atkins Inorganic Chemistry, 5th edition, a really important textbook for anyone wanting to understand the subject. Our goal for you, our curious listener, is to break down this complex topic step by step, making it clear, engaging, and easy to grasp without needing a single visual. Think of this as your essential guide to understanding the key principles that govern these unique compounds. And to truly appreciate where we are today, let's unpack a bit of history. Before the mid-1950s, D-block organometallic chemistry was pretty niche, but then came some groundbreaking discoveries. It's incredible to think that the very first D-block organometallic compound, Zeise's salt and ethene complex of platinum, was prepared way back in 1827. Imagine trying to understand that complex bonding with the tools they had back then.
It's truly fascinating, yeah. How these early discoveries like Zeise's salt or the first metal carbonyls such as tetracarbonyl nickel, discovered by Mond in 1890, they really offered these tantalizing hints of a rich field. But the real explosion, the aha moment that genuinely captured chemists' imaginations occurred much later, around the 1950s, with compounds like ferrocene.
And what a compound that was. Ferrocene, Fc5H52, discovered in 1951, truly changed everything. Its unique sandwich structure, where an iron atom is perfectly nestled between two five-membered carbon rings, and its remarkable stability completely defied the classical bonding descriptions of the time. It just didn't fit the existing rules.
Exactly. It was a profound puzzle. And that puzzle, that challenge to conventional wisdom, it really propelled the rapid development of this entire field. It ultimately led to Ernst Otto Fischer and Geoffrey Wilkinson sharing the Nobel Prize in 1973 for their independent but equally crucial contributions to understanding the bonding in these sandwich compounds. So let's start with a foundational definition. At its core, an organometallic compound contains at least one direct bond between a metal and a carbon atom, what we call an MC bond. This might seem simple, but it's a critical distinction. It sets them apart from many traditional coordination complexes that might contain carbon in their ligands but lack that direct metal-carbon connection, like something as common as cohen 33 plus with. Even cyanocomplexes, which do have MC bonds, are usually excluded because their properties, they align more with traditional coordination chemistry. It's a somewhat arbitrary line perhaps, but a very useful one, based on significant chemical and physical differences.
And what are some of those differences? How do these compounds typically behave compared to, say, inorganic salts?
Great question. Many organometallic compounds actually behave more like organic compounds than like typical inorganic salts. They often have surprisingly low melting points, with some even being liquid at room temperature. And unlike many inorganic salts, they're typically quite soluble in common organic solvents like tetrahydrofuran. This unique blend of properties is precisely why they're so versatile.
It's that versatility that makes this field so powerful. Now, when we talk about the unique nature of D-metal bonding, we're not just looking at simple sigma bonds as you'd find in Zaksher P-block organometallics. D-metals bring a whole new level of complexity to the table. We start seeing sigma, pi, and even delta bonds, especially when you consider how something like a cyclopentadenyl group bonds to an iron atom in ferrocene.
This immediately leads us to a crucial concept: stable electron configurations. D-metal organometallic compounds often show a strong preference for either 16 or 18 valence electrons around the central metal atom. This isn't just a random occurrence. It's deeply tied to those strong pi and delta bonding interactions with their carbon-containing ligands. In the 1920s, N.V. Sidgwick first recognized this pattern of stability, calling it the inert gas rule, though we now universally refer to it as the 18-electron rule.
So if I understand correctly, for an octahedral complex with what chemists call strong field ligands that really influence how the metal's d orbitals are arranged, you can accommodate 18 electrons in 9 bonding molecular orbitals. That's 6 from sigma interactions and 3 from pi interactions. Can you give us a classic example?
Absolutely. Take chromium hexacarbonyl, CrCO6. It's a colorless, air-stable compound precisely because it achieves that ideal 18-electron count. It is a large HOMO-LUMO gap, which means there's a significant energy barrier to either adding or removing electrons, making it exceptionally stable and unreactive.
So the 18 electron rule isn't quite like the octet rule for period 2 elements. It's not always strictly followed, right? The system seems a bit more flexible.
That's a crucial distinction. While 18 electrons signify high stability, compounds with fewer aren't necessarily unstable. Often, they are crucial intermediates in reactions, kind of eager to acquire those missing electrons. For instance, square planar complexes with strong field ligands, like those found in rhodium-1, iridium, palladium-2, and platinum-2 systems, they often find their most energetically favorable configuration at 16 valence electrons. This fills all 8 bonding molecular orbitals, leaving no antibonding orbitals occupied. Zeiss's salt, which we mentioned earlier, PtC2H4Cl3, is a perfect example of a classic 16-electron square planar complex.
That makes sense. So whether it's 16 or 18 electrons, there's an ideal. But why do we see exceptions? Is it always about the ligands?
Often, it is. Sometimes it's simply a matter of steric hindrance. You just can't cram enough ligands around the metal to reach 18 electrons without them bumping into each other. On the left side of the D block, metals start with fewer electrons, and if you combine that with bulky ligands, they might never reach for 16 or 18. Consider VCO6, a stable 17-electron complex. It's just too sterically crowded to dimerize and achieve 18 electrons on each vanadium center, even though that's what the rule suggests it should want to do. Given how important these electron counts are for predicting stability and reactivity, chemists need a reliable way to determine them. While there are a couple of methods, we'll focus on the donor pair method, which is widely used and helps us assign formal oxidation numbers to the metal. The key is how you classify your ligands. Some are treated as neutral, like carbon monoxide, CO, or phosphines, and they donate 2 electrons. Others are considered charged, such as halides, hydride H, or a methyl group, CH3, and they also donate 2 electrons each, but with a formal -1 charge. And then you have unique ligands like cyclopentadienyl, CP, which is treated as an anion, donating a full 6 electrons.
Okay, so once we've categorized the ligands, how does the actual calculation work?
First, you calculate the metal's formal oxidation number by subtracting the charges of all the ligands from the total charge of the complex. Simple enough. Then, you determine the number of electrons the metal itself provides, which is its group number in the periodic table minus its oxidation number. Finally, you just sum the metal's electrons with all the electrons donated by the ligands, and that gives you the total valence electron count. It's a bit like a chemical accounting exercise.
That's a really precise way to predict stability, even if, as you alluded to, the concept of oxidation state for organometallics can sometimes feel a bit like a useful fiction that helps the math work. Speaking of terminology, let's quickly talk about how we describe these compounds. Organometallic nomenclature follows similar rules to coordination complexes, but there's a special twist: hapticity.
Hapticity, that's crucial, yeah.
Indeed, it describes the number of ligand atoms that are formally bonded to the metal center, and we denote it using the Greek letter eta N. So a simple methyl group attached by a single MC bond is monohapto, or 8-1. If both carbons of an ethene ligand are bonded side-on to the metal, it's dihapto, 2. And for our old friend ferrocene, those cyclopentadienyl rings are fine 5, meaning all 5 carbon atoms of each ring are bound to the iron.
And don't forget bridging ligands. The Greek letter mu, is used to indicate how many metal atoms a ligand bridges. So a mu2CO means a carbonyl group is bridging 2 metals, and a bu-CO means it's bridging 3. Really helps paint a picture of the molecular architecture. Now let's delve into some of these fascinating ligands, starting with one of the true workhorses, carbon monoxide, or the carbonyl group. It's incredibly common and special because it's excellent at stabilizing metals in very low oxidation states. Its bonding is wonderfully synergistic. The carbon's lone pair acts as a weak sigma donor, giving electron density to the metal. But crucially, the metal then donates electron density back into Kiso's empty pi antibonding orbitals. This pi backbonding is incredibly strong and is the key to the stability of so many metal carbonyls.
So if the metal-carbon bond gets stronger due to this backbonding, what happens to the CO bond itself? Does it weaken?
Precisely. Increased backbonding weakens the triple bond within the CO molecule, reducing its bond order and causing its stretching frequency to decrease. This is something we can easily measure and observe using infrared spectroscopy. Terminal COs, those attached to a single metal, typically show up around 2100–1700 centimeters 1, while bridging COs, which are even more affected by backbonding, are found at lower frequencies, around 1900–1600 centimeters 1. It's a simple, elegant diagnostic tool for chemists. And remember, it's always considered a 2-electron neutral ligand, whether it's terminal or bridging.
While not strictly organometallic, because they don't always form direct metal-carbon bonds, phosphines are super important in this chemistry. Like Cézanne, they act as sigma donors from the phosphorus atom. but they're also pi acceptors, utilizing their empty sigma orbitals. What makes phosphines so special, though, is their incredible versatility. You can precisely tune their steric bulk, which is how much space they occupy around the metal, using something we call cone angles. Bulky phosphines, like tricyclohexylphosphine, PCI3, can effectively limit the number of other ligands around a metal, directly influencing the electron count and the geometry.
And beyond steric bulk, their electronic properties are inversely correlated. Electron-rich phosphines, like trimethylphosphine PMA3, are good sigma donors but poor pi acceptors, while electron-poor ones like phosphorus trifluoride PF3 are the opposite. This remarkable fine-tuning capability of phosphines is precisely what allowed chemists to design highly effective enantioselective catalysts. These catalysts could produce a single mirror image isomer of a drug molecule, fundamentally changing pharmaceutical synthesis by making complex chiral molecules accessible. It's a prime example of understanding a ligand's properties leading to groundbreaking applications. Hydrogen can also bond to metals in two truly fascinating ways. A hydride ligand, H, forms a simple, strong sigma interaction with the metal, acting as a 2-electron donor. But what's truly remarkable are dihydrogen complexes, where the entire H2 molecule bonds side onto the metal without breaking the H-H bond. This involves sigma donation from the H2 bond to the metal, and then pi back donation from the metal into the H2's empty sigma antibonding orbital. If that back bonding becomes extensive enough, it can actually weaken the H-H bond so much that it essentially breaks, forming two separate hydride ligands, a process we call oxidative addition.
So you can literally observe the transition from an intact dihydrogen molecule to two distinct hydrides, and in doing so, the metal's oxidation state increases by 2. That's a huge insight linking a fundamental bonding concept directly to a major reaction type. Wow. Moving to other core carbon-based ligands, the simplest are those that bond through a single carbon atom, making them monohapto or eke1. Think of ligands like methyl, ethyl, phenyl groups. Their MC bonding is a straightforward sigma interaction. But watch out for a common decomposition pathway here called beta-hydrogen elimination, where a hydrogen atom on the carbon adjacent to the metal can migrate to the metal, often making these alkyl groups less stable.
Building on that, alkenes and alkynes typically bond side-on, or point 2, utilizing their pi bonds. This interaction is elegantly explained by the Dewar-Chat-Duncanson model. The alkenes-filled pi bond donates electron density to an empty metal orbital, forming a sigma bond. Simultaneously, a filled metal orbital donates electron density back to the alkene's empty pi antibonding orbitals, forming a pi bond. This back bonding can significantly weaken the carbon double bond, pushing it towards a single bond, almost like forming a 3-membered metallocyclopropane ring around the metal.
And what are the implications of that weakened CSE bond? Makes it more reactive.
Exactly. It means the alkene becomes activated for further reactions, making these complexes crucial intermediates in many catalytic processes like polymerization or hydrogenation, where you're ultimately breaking or forming new carbon-carbon bonds.
Beyond these, we see many other versatile Soder ligands. Non-conjugated dienes, like cyclotoca 1, 2, or 5 diene, often called COD, are treated almost like two independent alkenes, but their linked structure provides increased stability due to entropy effects. Sort of keeps them nearby.
Right. Then there are fascinating ligands like butadiene and cyclobutadiene, which are 4-electron-neutral donors, and the aromatic benzene, an 0.6 ligand that donates 6 electrons. The bonding here can become quite intricate, involving combinations of sigma, pi, and even delta back bonding from the metal into the ligand's antibonding orbitals. It gets complex quickly.
And the allyl ligand, CH2, is incredibly flexible, capable of switching between an 0.1, a 2-electron donor, and an up3, a 4-electron donor form. This flexibility often makes 0.3 allyl complexes highly reactive, allowing them to bind to other ligands and participate in many transformations.
And of course, the cyclopentadenyl anion, C5H5, or CP, is particularly iconic. It's an aromatic 6-electron donor, typically binding as 0.5. Its remarkable stability and symmetrical structure are explained by its molecular orbitals, which involve a balanced mix of sigma and pi donation and delta back bonding. This ligand, especially in metallocenes like ferrocene, truly transformed our understanding of organometallic bonding, showing us how incredibly stable these electron-rich systems could be.
The diversity of lichens just keeps expanding. We have carbenes, for instance, which are highly reactive species with either electron-deficient or electron-rich character, leading to distinct types like Fischer and Schrock carbenes, each with unique reactivity. And the surprises keep coming. Even seemingly inert alkanes can subtly interact with a metal through their CH bonds, forming what we call agostic interactions. These fleeting connections are crucial because they're often the very first step a metal takes in breaking those incredibly strong CH bonds, a kind of holy grail in sustainable chemistry for upgrading simple feedstocks like methane.
And the list continues. Did nitrogen, N2, and nitrogen monoxide, NO, are also found as ligands. N2 being electronically similar to CO, bonds similarly but generally more weakly. NO is a radical, and its bonding is especially versatile. It can bind in either a linear fashion, acting as a 3-electron donor and formally NO plus CO, or in a bent fashion, acting as a 1-electron donor and formally NO. This makes it a fascinating, if sometimes challenging, ligand for electron counting. And incredibly, even noble gases like xenon can weakly coordinate to a metal center when no other ligands are available, though these interactions are very fragile. Building on our discussion of ligands, D-block carbonyls are a cornerstone of organometallic chemistry. Homoleptic carbonyls, meaning those with only CO ligands, beautifully illustrate the 18-electron rule. For instance, CrCO6 is octahedral, FCO5 is trigonal bipyramidal, and NiCO4 is tetrahedral. For odd group elements like manganese, dimerization with a metal-metal bond, as seen in Mn2CO10, helps each metal achieve that stable 18-electron configuration.
So, beyond just illustrating electron rules, what makes them so important in the grand scheme of organometallic chemistry? Why focus on them?
Well, they're incredibly versatile. They often serve as crucial precursors for synthesizing a whole host of other organometallic compounds. Their synthesis methods vary too, from simply combining the metal directly with CO under pressure to reductive carbonylation, where a metal salt is reduced in the presence of CO, essentially forcing the carbonyls onto the metal.
And their properties, are they unusual?
Quite distinct. Many are volatile, soluble in organic solvents, and some polynuclear carbonyls. Those with multiple metal centers exhibit vibrant colors due to electronic transitions within the metal framework. They also undergo a range of fascinating reactions, including oxidation, reduction to metal carbonylates, which are essentially anionic metal carbonyl complexes, and even disproportionation reactions.
And the CO ligand itself can be quite reactive, not just a passive spectator ligand.
Absolutely. The carbon atom of the CO ligand is susceptible to nucleophilic attack if the metal is electron poor, leading to the formation of compounds like Fischer carbines. Conversely, in electron-rich carbonyls, the oxygen atom can be attacked by electrophiles, especially when the CO is in a bridging position. This dynamic reactivity means CO is not just a building block, but an active participant in many transformations. And again, IR spectroscopy is an incredible tool here, giving us insights into the symmetry and bonding of these complexes by analyzing the number and frequency of their CO stretching bands.
Let's circle back to ferrocene for a moment. It's the archetype of what we call sandwich compounds, or metallocenes, where a metal atom is truly sandwiched between two planar carbon rings. These compounds are incredibly stable enough to undergo organic-like reactions directly on the ligand rings, such as Friedel-Crafts acylation or lithiation. It's like having an organic molecule with a metal in the middle, ready to be functionalized.
The molecular orbital picture for ferrocene beautifully explains its 18-electron stability. What's crucial here is that the frontier orbitals, the highest occupied and lowest unoccupied, are neither strongly bonding nor strongly antibonding. This means they're sort of non-committal electronically, allowing for a surprising robustness and flexibility. This feature allows for stable metallocenes that do deviate from the 18-electron rule, such as the 17-electron FeCP2 plus concation or the 20-electron NiCP2, with predictable changes in bond lengths and redox properties.
That flexibility is fascinating. And many metallocenes exhibit what's called fluxionality, meaning the rings rapidly rotate or the metal-ligand bond whizzes around the ring, even at room temperature. This dynamic behavior can be observed and studied using NMR spectroscopy, giving us a window into their constant internal motion, like little spinning tops.
Moving beyond single metal centers, we encounter metal clusters, compounds with multiple metal bonds forming triangular, linear, or larger polyhedral structures. These are fascinating because their properties often resemble tiny pieces of metal surfaces, making them highly relevant for understanding heterogeneous catalysis. For smaller clusters, the 18-electron rule can be adapted. A cluster of X metal atoms with Y metal-metal bonds needs 18X minus 2Y electrons. For larger, more complex clusters, the Wade-Mingo's-Lauer rules provide a powerful framework for correlating the cluster valence electron, CVE count, with specific polyhedral structures. It's a whole other level of electron counting.
And this is where isolobal analogies really shine. They allow us to connect fragments of molecules that have similar orbital symmetries and electron occupations, even if they look completely different on the surface. It's like finding unexpected chemical relatives, allowing us to rationalize incredibly diverse structures, from organic cages to complex metal clusters. It's a testament to the underlying principles of orbital theory. Really elegant. Now let's turn our attention to the dynamic world of organometallic reactions. Just like traditional coordination complexes, organometallic compounds undergo ligand substitution, where one ligand is replaced by another. The key difference, though, is the constant striving to maintain that ideal 16 or 18 electron count.
Precisely. Reactions can be dissociative, where a ligand leaves first, creating a vacant site, which is typical for stable 18-electron species. Or they can be associative, where an incoming ligand binds first, which is common for 16-electron species that can easily accommodate an extra ligand temporarily. Steric crowding plays a huge role here. Bulky ligands can speed up dissociative processes, but slow down associative ones. And sometimes even 18-electron complexes can undergo associative substitution if a ligand, like CP or NO, can momentarily slip or change its bonding mode, temporarily reducing the electron count and creating a transient vacant site. Clever trick. These next two reactions, oxidative addition and reductive elimination, are perhaps the most important reactions in organometallic chemistry, especially when we talk about catalysis. Oxidative addition involves a molecule, let's say XY, adding to a metal. It breaks the XY bond and forms new MX and MY bonds. This dramatically increases the metal's coordination number by 2, and crucially, its formal oxidation state by 2.
So it's literally the metal being oxidized as it gains two new formal ligands. And the reverse of this, reductive elimination, is when two ligands couple together and leave the metal center, which reduces its coordination number and its oxidation state. These reactions are often reversible and are the fundamental engines that drive many catalytic cycles. They're like the forward and reverse gears. Sometimes, when oxidative addition isn't energetically favorable, maybe for complexes of early D metals, a different kind of exchange happens, that metathesis. It's a concerted process, often involving a four-membered transition state where two sigma bonds essentially swap partners. For example, a metal hydride and an alkane could exchange an alkyl group and a hydrogen atom without going through an oxidative addition intermediate.
Then we have a one-var-on-one migratory insertion reactions. This is a fascinating rearrangement where a group, typically a hydride or an alkyl, migrates from the metal to an adjacent ligand, most commonly a carbonyl group. So a methyl group and a CO ligand might combine to form an acyl group like -COCH3. This reaction always decreases the electron count on the metal by 2, but leaves the oxidation state unchanged.
And the amazing thing, which was discovered through clever experiments, is that it's the alkyl group that physically moves to the CO, not the CO inserting itself into the MC bond. And critically, the stereochemistry of the migrating group is preserved, telling us a lot about the mechanism. Really neat detective work.
Similarly, 1,4,2 insertion involves a group migrating to an atom 2 bonds away on a ligand, like an alkyl or hydride migrating to an alkene. This forms a new alkyl group on the ligand, and again, the metal's electron count decreases by 2 with no change in oxidation state.
Well,
This is fundamental to polymerization reactions, where you're essentially adding monomers one after another, chain growth.
and the reverse of that, hydride elimination, where a hydrogen on the beta carbon moves back to the metal, is a common decomposition pathway for alkyl complexes, often leading to the formation of alkenes. It's also a key step in alkene isomerization, where double bonds shift positions, a common problem, or tool, depending on context. Finally, we have other types of hydride eliminations, alpha, gamma, delta, epsilon, which are often grouped under cyclometallation reactions. These involve the metal inserting into a CH bond further down a ligand chain, forming a new metal cyclic ring. It's like the metal reaching out and grabbing a remote part of its own ligand to form a new, more stable ring structure. So what have we learned from this exploration into D-metal organometallic chemistry? It's been quite a journey. We started with a rich history of surprising discoveries, from Zeis's salt to the groundbreaking ferrocene. We explored the unique bonding principles, especially the importance of the 16 and 18 electron rules and how to count them. We examined a diverse array of ligands, from the ubiquitous carbonyl to the dynamic cyclopentadienyl, each with its own special way of interacting with the metal center and giving these complexes their unique personality. And we broke down the key reactions, substitution, oxidative addition, migratory insertion, and more, which define how these compounds transform and ultimately how they drive so much of the chemistry around us.
If we connect this to the bigger picture, you've now gained a foundational understanding that empowers you to look at a chemical reaction and predict its course. or even to begin thinking about how to design entirely new catalysts. This knowledge isn't just for exams. It's a critical lens for viewing and shaping fields, from sustainable energy and environmental remediation to pharmaceutical synthesis and advanced materials. This raises an important question. How will you, with this new understanding of these fundamental principles, apply them to solve the next generation of chemical challenges? Where do you see this going?
Consider this. The incredible versatility and fine-tuning possible in organometallic chemistry allow us to imagine a future where chemical reactions are not only more efficient but also precisely controlled, generating minimal waste and yielding entirely new materials with unimaginable properties. What overlooked combination of metal, ligand, and reaction pathway might be waiting in the lab just around the corner to unlock the next major scientific breakthrough? Something to think about. Thank you for joining us on this deep dive. We hope this exploration has been as enlightening for you as it was for us. Keep learning, keep asking questions, and until next time, this has been your Last Minute Lecture Team, signing off.